Wireless communication is a journey. It's the process of taking information stored as bits at the source and transporting it through the air to a user. We start with a stream of bits, zeros and ones. But the air actually doesn't understand ones and zeros. It understands the physics, the waves. So our first challenge is how we translate these digital numbers into something physical. To answer that, we need to look at the carrier signal, the cosine wave. Mathematically, we have three distinct knobs we can turn to change this wave. First, there is the amplitude, the A. Notice how changing this value stretches or squishes the wave vertically. It represents the signal's strength. Next, there is the frequency, F in Hertz. This controls how fast the wave oscillates. Let's say the pitch of the signal, if you will. And finally, we have the phase. This shifts the phase or the wave horizontally in time, changing where the cycle began. We can use these properties to encode our data in amplitude shift keying. We map beats to a height. For example, a 1 is a loud wave, a 0 is a quiet one. Alternatively, with frequency shift keying, we use the speed. For example, a 1 vibrates faster, while a 0 vibrates slower. But there is a more elegant approach often used in modern systems, which is the BPSK, or the binary phase shift keying. Here, we keep the amplitude and the frequency constant, but for a 0, we flip the wave by 180 degrees. Let's look closer at the math behind BPSK. Bit 1 is a standard cosine wave, and bit 0 is the same wave just shifted by pi. So, mathematically, cosine of theta plus pi is just a negative cosine. This gives us a beautiful geometric intuition. So we can stop thinking about wiggling waves and start thinking about vectors. On this complex plane, the I and Q plane, we can map bit 1 as a vector pointing to the right and bit 0 as a vector pointing to the left. We have effectively turned our calculus problem into a geometry problem. Now, we must introduce the craziest part of our story, the channel. In the real world, signals are never perfect. Thermal noise adds random interference to our transmission. Geometrically, this noise doesn't just nudge the signal actually, it scatters it. Instead of landing on that perfect 1 or 0 points, our receiver or our received signal lands somewhere within a cloud of probability surrounding the target. So how does the receiver make sense of this messy data? It makes a decision based on regions, actually. So the receiver draws a line in the sand, a decision boundary right down the middle. If the signal lands on the right, it assumes we sent a 1. Even if the point is imperfect, as long as it stays on the correct side, the data is preserved. But the probability is a tricky thing. Sometimes the noise is strong enough to push the point all the way across the boundary. Here we sent a 1. The vector belongs on the right, but the noise vector was so strong to the left that the receiver sees it in the orange region. So it creates a bit error. This is the reality of the final output. We reconstruct the stream. Most bits survive the journey intact, but look at that last bit. The user receives a 0 instead of 1. This entire field of engineering essentially is about finding ways to keep those points on the correct side of that line.